thermometer. If we take our digital thermometer and put our digital thermometer into the nitrogen, we'll just read the numbers on the side that will tell me exactly how cold it is. Ready?
Yep.
Okay. Here we go. Okay. So, in 3, why are you covering your ears? It's a thermometer. What?
It's a balloon.
Are you sure? Okay. I couldn't fool you. Yes, it is in fact a balloon. I was hoping you wouldn't really pay attention to that part, but I spent most of my money, most of my budget on the show on liquid nitrogen. I couldn't afford a thermometer. All I have is this balloon. But I'm pretty sure a balloon is a good thermometer, at least a very good homemade thermometer, because if you put a balloon into boiling hot water, what do you think it will do? Exactly. It will pop, it will lose all of its air. And since this balloon is going to go into very cold liquid nitrogen, it will not pop and lose its air. It will just frost over, get very, very chilly, and freeze. So you don't have to... You know what? This is actually a good thing this has happened, because this is also a show about the scientific process. Right? We've been doing the show for a long time, and we like to use it to teach about how we do experiments here. If you're doing an experiment and something goes wrong, there's a mistake, an accident happens, do you think that you should take the very first result that you get from that and say that's a fact?
No.
Probably not, right? If something goes wrong, you should try your experiment again. So you know what we're going to do? We're just going to discard this balloon. We're going to do one. We'll just try a new balloon. So let's go grab a new thermometer. Here we go. This time we'll take a new thermometer. We put our new thermometer into the nitrogen. Well, it's a new one, yeah. Oh, okay. I think I see what happened here. Let's try that again. If we put our balloon into the nitrogen, it deflates. Let's put the second one in there too. See if the same thing happens. Yeah. Okay, so we put the balloon into the nitrogen, it deflates. However, have you ever popped a balloon and then watched it on its own reinflate? It's kind of hard for balloons to do that, right? You have to force an air into a balloon. It's not just going to flow in there on its own. So if I take these out of the nitrogen and they inflate, it's not because the air is going back in. It's because we did something to the air on the inside. So let's take a look at our states of matter again and break them down into some really small chunks. Everything around us, like you, me, the nitrogen, the balloons, my gloves, my nose, this sign, are all made of these tiny, 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 tiny little particles. And what do we call these little small things? Yeah. These small things are smaller than cells, smaller than germs. Not the smallest thing we've discovered, but still pretty small. We call these things atoms, little tiny atoms. Now, if I wanted to show you a single atom here on stage, well, stay there. Okay. Here we go. Ready? If I take out this little tiny speck of dust right here, there are billions of atoms in that little tiny speck of dust. These things are way too small for me to show you. I mean, maybe if I had some really expensive microscopes, but if that's what I'm using as a thermometer, don't expect me to have one of those microscopes here. So instead, what we're going to do to show you what these atoms are doing, how they're behaving in the balloon, we need a model. This is called a Hoberman sphere. You might have played with one. It's a really cool toy. But the Hoberman sphere will help us learn about atoms. If we pay attention to the green things on the outside and pretend that these green things are the atoms that make up the air in that balloon, well, if we give them energy, do you think giving them energy is making them heat up or cool down? They heat up, right? If we give them this energy, they're heating up. And as they get hotter and hotter, they move faster and faster. And as they move faster and faster, they start to spread further and further and further apart. So giving our atoms energy, heating them up, makes them move fast, spreads them apart, makes them go crazy. Well, this means if we take a look at a liquid, right? If you heat up a liquid, it starts bubbling and steaming, and it turns into a gas. This is what we're seeing happen. If you give this water energy and heat it up, we're turning it into its gas state because those atoms are spreading further apart. And the further they spread, the easier it is for them to move. So if we're dealing with a liquid, let's go the other direction now. If we take away that energy and cool it down, do you think they keep spreading? No. Instead, they slow down. And the slower they get, the harder it is for them to move, and the closer they get to each other. And then you've got a solid, okay? So bringing our atoms closer and closer together means it's harder for them to move, and now you have something that's got more form and structure to it. And now imagine if I stuck my head into a bucket of water. It would get wet, but I could easily take it out because those atoms are moving a lot easier than they are in their frozen solid state. All right, let's bring this back to our balloon. We put this balloon into the liquid nitrogen, and we can watch as that balloon shrivels up. Not because the air is coming out, but because the atoms inside that air are doing what? Coming closer, right? Condensing on the inside. Those atoms are coming closer, which means taking up less space on the inside. Now, maybe even some of the gases in the air are turning into liquid on the inside of this balloon. When we take it out, since our nitrogen is so cold, the air around you, as chilly as it feels in this museum, is warm enough to cause those atoms to spread apart. So that means that our liquid nitrogen is in fact very cold. But it is so cold, it's doing something that water will do when it reaches 212 degrees Fahrenheit. Let's take a look at temperature, right? If we